us consider speed of a wave. Under this caption, we are going to deal with what is the basic equation for calculating the speed of a wave, and on what other factors the speed of sound in particular that depends. So, two different aspects we are going to take up here. Whenever we talk about speed of a wave, general statement is this: speed is displacement divided by time. Rate of displacement of the body, we used to call it as speed. Of course, ds by dt we used to write it. Now, we can rewrite the same in this case. When I consider a wave like this, its total length is going to be taken as lambda, and the time period corresponding to that lambda is called t. Therefore, we can write this one as lambda over t. But in fact, we can all understand the reciprocal of time period is frequency. Therefore, we can write v is equal to n lambda. This is actually the equation one has to remember as far as speed of a wave that is concerned. But in this regard, n refers to frequency of that vibrating body which is producing the sound. As an example, like we shall take up that way. Now, when v is n lambda, whenever a wave is entering from one material medium into another, in other words, whenever refraction of a wave that takes place, refraction of course we are all aware of, bending either towards the normal and travelling in the second medium, or bending away from the normal and travelling in the second medium. So, whatever be the case, whenever refraction of light that is taken place or refraction of sound that is taking place, then frequency is the only physical quantity or the parameter of the wave which remains constant. So, when frequency remains constant, we can understand directly this way that v is directly proportional to lambda. So, this is the relation one need to remember between the speed and corresponding wavelength when frequency remains constant. That in other words, you can say in denser medium, wavelength decreases, then automatically speed also is going to be decreased. So, that is the general concept of things what we used to consider in the form of light. So, general equation is this: whenever refraction that takes place, the frequency is the only parameter which remains constant. Remember that concept 1. Now, on what factors the speed of sound that depends? Now, we are concentrating on the speed of sound here. So, we can understand now this way: factors that affect speed of sound. That is actually the concept what we have to consider. Now, if you take this factors which will affect, very first concept we need to understand is about Newton's formula. This Newton's formula is actually meant for calculating speed of sound in an isothermal medium. What he has predicted, if the material medium is isothermal, where of course the temperature that remains constant, and quantity of heat of course is a variable, but temperature remains constant is the major criteria one has to consider here. So, in an isothermal material medium, speed of sound mainly depends on two factors according to him. One, it is directly proportional to square root of modulus of elasticity of the medium, and inversely proportional to square root of density of the medium. So, one can understand in this particular case, when the medium is highly elastic, sound travels faster in that medium. When the medium's density is very low, then sound travels faster in that medium. So, two aspects of course he has taken up under the condition that the temperature of the medium should be constant. In other words, one can say for an isothermal medium, this is the case on which of course the speed of sound that depends. These are the factors. Now, if I just generalize that equation, I can write V is equal to under root E by rho. That E of course is modulus of elasticity. Suppose if I consider a gaseous medium, I can rewrite the same this way as well, under root K by rho. What is this K over here? That is what we call it as bulk modulus of elasticity of that gaseous medium. Now, bulk modulus of elasticity K, or generalizing that equation as modulus of elasticity E, anything we can write in that formula, that V is equal to under root K by rho. But in general, in isothermal medium, observe this wording. In isothermal medium, modulus of elasticity, either you can write bulk modulus or generalizing that one as modulus of elasticity E, that is numerically equals to the pressure of the medium. What exactly is this concept? Isothermal modulus of elasticity is equal to pressure. That is the relation. So, how come you be getting this one direct application? In fact, we know when we take PV is equal to constant, when temperature is kept constant, this in fact is taken as Boyle's law. Now, when I just differentiate this one, PdV plus VdP is equal to 0. In other words, we can write PdV is equal to minus VdP. In other words, we can rewrite the same as P is equal to dP by dV by V in the denominator. That in fact we can understand this is nothing other than pressure by volume strain. In other words, pressure by bulk strain. That itself we call it as bulk modulus of elasticity. So, what I can write directly in this case now? Bulk modulus of elasticity and pressure both are numerically equal. For what condition? If the material medium is isothermal. Then directly I can write the same equation this way as under root P by rho. And pressure of air if you consider, and density of air if you consider, and if you simplify this particular value for V at 0 degrees centigrade, what these people have got is 280 meter per second they have got in air at 0 degrees centigrade. At 0 degrees centigrade, speed of sound in air, they have got 280 meter per second, whereas the practically obtained value is 330 meter per second. In fact, it is 330 to 332 meter per second. It varied in between. So, naturally, this is 280 meter per second and that is 332 meter per second. It's a wide variation. That means there is something wrong with the idea that has been taken by Newton. What is this concept? Where he has gone wrong means the very simple concept here is considering the medium to be isothermal itself is a wrong concept. What for means whenever sound is entering into a medium. Initially, the temperature of the medium may be constant, no doubt absolutely in that. The moment sound wave enters, compressions and rarefactions are going to be formed in the system. In fact, we all know compression is that zone where the pressure is maximum, and rarefaction is that particular zone where the pressure is minimum. When you just compare a compression with rarefaction, there will surely be slight difference in the temperature at the compression and at rarefied zones. That means, at compression, the temperature is a little higher than the zone what we are calling it as a rarefaction or rarefied zone. So, the moment there is a variation in temperature, one cannot consider that material medium as isothermal. So, isothermal material medium you can call it only when temperature throughout the medium is constant. But here when temperature is a variable, whether it is slightly varying or highly varying, whatever it is immaterial for us. According to physics, will there be variation in temperature or not? Of course, yes. When you are considering there is a variation in temperature like that, automatically one should not consider that medium as isothermal medium. So, one should consider that one as adiabatic medium as such. So, considering the material medium to be adiabatic, Laplace has just given a small modification to the equation which has been given by Newton. That is what actually we call it as the Laplace's correction. He simply has corrected the equation given by Newton. What is that correction? Let us have a look.